Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently toward one of the strangest objects the universe can make, a neutron star. For now, imagine that you are far from Earth, drifting through a quiet field of stars. Ahead of you, there is a point of light that does not seem dangerous at first. It is small, faint, almost easy to overlook. But as you move closer in imagination, that ordinary point begins to gather meaning. It is not a planet. It is not an ordinary star. It is the collapsed core of a massive sun, compressed until more mass than our sun can fit inside a sphere only about the size of a city. From a safe distance, the first surprise is not how large it is, but how small. A neutron star may be only about 20 kilometers across. On Earth, that is the scale of a city or a long drive across a familiar landscape. In space, it is almost nothing. And yet this small remnant may contain 1 or 2 times the mass of the sun. That is the first lesson of the journey. The danger is not spread across a glowing sphere millions of kilometers wide. It is folded inward. The star has become compact, dense, and almost impossibly intense. To understand what that means, bring your attention back for a moment to the room around you. The floor, the walls, the air, and your own body all seem solid and ordinary. But matter is not solid in the simple way it appears. Atoms are mostly empty space, with tiny nuclei surrounded by much larger regions occupied by electrons. If an atom were enlarged to the size of a stadium, its nucleus would be more like a small bead near the center. So why does the world feel solid beneath you? Not because atoms are packed like stones in a wall. Matter feels solid because electrical forces and quantum rules prevent atoms from simply passing through one another. The surface beneath you is an arrangement of fields, charges, and rules, holding its shape so consistently that your body can trust it. Now return to the neutron star. In that collapsed remnant, gravity has pressed matter beyond the familiar architecture of atoms. Electrons are driven into protons. Neutrons form in enormous numbers. The spacious structure of ordinary matter is crushed away, leaving material at densities comparable to an atomic nucleus but extended across an entire star. This is why the usual comparisons sound unreal. A teaspoon of neutron star matter, if it could somehow be brought to Earth and remain stable, could weigh roughly 1 billion tons. The image is memorable, but it is also impossible in a practical sense. No hand could hold it. No spoon could contain it. Without the crushing pressure of the star itself, that matter would not remain a neat sample from a cosmic laboratory. Still, the comparison helps your mind approach the scale. Imagine a mountain hidden inside something small enough to fit in your palm. Then imagine that this was only the beginning. As you drift closer in thought, gravity becomes the next sign that this object is no ordinary star. Near the surface, gravity may be about 100 billion times stronger than it is on Earth. An object falling toward the star would not merely drop. It would accelerate to a significant fraction of the speed of light before striking the surface. Falling near a neutron star is not a gentle motion. It is an astrophysical event. The gravity also changes the view. According to general relativity, mass curves space-time, and light follows that curved geometry. Around a neutron star, the bending can be strong enough that more than half of the surface may be visible at once. Light from the far side can curve around into view. The star partly reveals what should have been hidden. Time changes there as well. A clock near the surface would run more slowly compared with a clock far away. The clock is not broken. Time itself is passing differently in the strong gravitational field. Light escaping from the surface loses energy as it climbs outward, stretching toward longer, redder wavelengths in a process called gravitational redshift. And still, for all this extremity, a neutron star is not a black hole. That difference matters. A black hole has an event horizon, a boundary beyond which no signal can return. A neutron star still has a surface. Radiation can still leave it. Matter can still strike it. Gravity has nearly finished the work of collapse, but something inside the remnant still resists. That resistance is one of the central mysteries of neutron star physics. Quantum mechanics, nuclear forces, relativity, magnetism, and the behavior of ultra-dense matter all meet inside this small object. No spacecraft could land there. No probe could drill into it. Scientists study it by reading what escapes: pulses, X-rays, gravitational waves, neutrinos, mass measurements, radius estimates, and the timing of distant signals. The star becomes a sealed laboratory. It does not open itself to us, but it leaves clues. Some neutron stars rotate hundreds of times every second. Some carry magnetic fields trillions of times stronger than Earth's. Some send beams of radio light across the galaxy with the regularity of natural clocks. Others feed from companion stars, produce X-rays, flare as magnetars, or collide with another compact remnant and help create elements such as gold and platinum. They are often called dead stars, but that phrase is too small. Fusion has ended in their cores, yes, but their stories are not over. A neutron star can shine, pulse, cool, feed, flare, merge, and wander through the galaxy for millions or billions of years. To understand where such an object comes from, we have to move backward in time, before the point of light, before the collapsed city-sized remnant, before the pulses, the magnetic storms, and the impossible density. We have to enter a star far larger and more luminous than the Sun, while gravity and fusion are still holding one another in balance. For millions of years, that balance can endure. Then, deep inside the core, the fuel begins to change. Imagine the neutron star before it was a neutron star. Not as a compact point in the dark, but as a massive living star inside a cloud of gas. The cloud is mostly hydrogen, with helium and traces of heavier elements left by older stars that lived and died before it. At first, the gas is cold and diffuse, spread across distances so wide that the mind struggles to hold the shape of it. But gravity is patient. A slightly denser region gathers more material. More material strengthens the pull. The center contracts, heats, and grows brighter as gravitational energy becomes heat. At first, the young object shines only because it is shrinking. Then the core becomes hot enough for hydrogen fusion, and the object becomes a true star. In a massive star, this beginning is magnificent. the core reaches extreme temperatures. Hydrogen nuclei collide with enough force to overcome their electrical repulsion and fuse into helium. Energy flows outward. Gravity pulls inward. For a time, the star becomes a bright negotiation between collapse and light. From far away, you might see a blue-white star blazing inside a nebula, pouring ultraviolet radiation into surrounding gas. Its light carves cavities in the cloud around it. Its stellar wind pushes material outward. Hydrogen gas glows in broad red and pink regions as radiation strips and restores electrons. Long before the star dies, it is already reshaping its environment. But deep inside, the clock is running. This is one of the strange facts of stellar life. The largest stars do not live the longest. They live intensely. A star 10 or 20 times the mass of the sun may shine tens of thousands or hundreds of thousands of times more brightly. It spends its fuel extravagantly, as if brilliance itself were a countdown. For millions of years, hydrogen fusion can continue in the core. Then the hydrogen becomes depleted. Fusion pressure weakens, the core contracts, and contraction raises the temperature. At higher temperatures, helium fusion begins. Helium nuclei combine to form carbon and oxygen, and the star changes again. If you could somehow look inside, the star would no longer be simple. Hydrogen may still burn in an outer shell. Helium may burn beneath it. Deeper still, carbon, neon, oxygen, and silicon can burn in separate stages. The interior begins to resemble an onion, but an onion made of fire, pressure, and nuclear transformation. This image is beautiful, but it is not peaceful. Each new fuel lasts for a shorter time than the one before. Hydrogen burning may last millions of years. Helium burning may last hundreds of thousands. Carbon burning may be far shorter. By the time silicon begins fusing into iron group elements, the final stage may last only days. The star that once seemed stable across cosmic ages is now racing toward its end. The reason is iron. For most of the star's life, fusion releases energy. Light nuclei combine into heavier ones, and a small amount of mass becomes energy. That energy creates pressure, and pressure resists gravity. But iron sits near the peak of nuclear binding energy. Fusing iron into heavier elements does not release useful energy. It consumes energy. When an iron core forms, the star has reached a dead end. Its central engine can no longer answer gravity by ordinary fusion. The outer layers still press inward with immense weight. The core has no new source of energy strong enough to hold them back. The great balance begins to fail. Think of a vast structure held up by a furnace beneath it. As long as the furnace burns, pressure rises and supports the weight above. But if the furnace suddenly stops, the weight does not wait politely. It falls. In a massive star, the weight is not a building. It is layer upon layer of stellar matter pressing inward from every direction. When the iron core can no longer support itself, collapse begins. This collapse is not slow. It is not a crumbling over centuries. It is a catastrophic implosion. Matter that once occupied a region thousands of kilometers wide falls inward toward a sphere only tens of kilometers across. In less than a second, material can plunge toward the center at a significant fraction of the speed of light. During this fall, atoms are destroyed as recognizable structures. Electrons are forced into protons, producing neutrons and neutrinos. The neutrinos are tiny particles that interact so weakly with matter that they can pass through entire planets, almost as if the planets were not there. But inside the collapsing core, they are made in overwhelming numbers. Most of the energy of a core collapse supernova does not leave as visible light. It escapes as neutrinos. This changes how the event should feel in your imagination. The brilliant explosion seen across space is only the visible surface of something deeper. The real energy flood streams outward in particles that barely notice ordinary matter. If your eyes could see neutrinos, the death of a massive star would be one of the brightest events in the universe. As the core collapses, density rises until atomic nuclei are driven together. Neutrons form in enormous numbers. Eventually, the collapse is resisted by forces rooted in quantum physics and nuclear physics. Matter cannot simply be compressed without limit unless gravity is strong enough to make a black hole. In many cases, the stiffening core rebounds and helps launch the supernova. The outer layers, still falling inward, collide with the newly compact center and are blasted outward. The explosion tears the star apart. Elements forged during the star's life, along with new elements created in the explosion, scatter into space. This is how stars recycle matter. The oxygen we breathe, the calcium in bones, the iron in blood, and many atoms beneath our feet were formed in earlier generations of stars. A massive star does not simply die. It returns its interior to the galaxy. Its collapse becomes a gift to the future, spreading enriched material through space where gravity may one day gather it again. Endings become beginnings. But not everything is thrown away. At the center of the explosion, the collapsed core remains. If it is not massive enough to become a black hole, it stabilizes as a neutron star. It is newly born, incredibly hot, rotating rapidly and wrapped in a magnetic field intensified by collapse. What was once the central region of a giant star is now a compact world of nuclear density. The birth of a neutron star is therefore both destruction and creation. A star dies in a supernova, but a new object appears. The visible supernova fades. The expanding debris cools. The surrounding gas becomes a nebula, glowing for a time as it spreads into space. But the neutron star can remain, spinning in the center or racing away from the explosion that created it. Some newborn remnants receive a powerful kick during birth. If the blast is stronger in one direction, the compact core can recoil in the other, flying through the galaxy at hundreds of kilometers per second. Even in death, stars can move. Picture it now, an ember flung from a cosmic fire. Except this ember is denser than an atomic nucleus, hotter than imagination, and heavier than the sun. Its journey may last for millions of years. It carries the memory of the giant star that came before it. And as it turns, the dead core begins to reveal a new kind of life. Stay with the newborn remnant for a moment. The supernova expands behind it, but the compact core remains almost impossibly concentrated. It is hot. It is dense. and it is often spinning. The spin is not accidental. Before collapse, the star's core already carried angular momentum. When that core shrank from thousands of kilometers across to only about 20 kilometers across, its rotation intensified dramatically. You know the everyday version of this principle from a skater pulling in their arms. The mass moves closer to the axis and the spin becomes faster. A collapsing stellar core does the same thing on a cosmic scale. Matter rushes inward. The radius shrinks. The rotation rate rises. But a neutron star is not a skater. It is a sphere of nuclear density matter with crushing gravity, extreme magnetic fields, and a surface where even a tiny mountain could contain an immense amount of mass. Some neutron stars rotate once every few seconds. Others rotate many times each second. The fastest known pulsars can turn hundreds of times per second so quickly that their surfaces move at enormous fractions of the speed of light. Imagine standing impossibly far away, protected from radiation and gravity, watching the star as a lighthouse rather than a world. Its magnetic axis does not have to line up with its rotation axis. Radiation can stream from regions near the magnetic poles. As the star spins, those beams sweep through space. If one of them crosses Earth, radio telescopes detect a flash. This is a pulsar. The star is not pulsing because its whole body expands and contracts. It appears to pulse because the beam reaches us once per rotation, like the lamp of a lighthouse crossing a distant shore. The regularity can be astonishing. Some pulsars behave like cosmic clocks, with pulses arriving so steadily that tiny deviations become meaningful. Astronomers can use those deviations to study motion, gravity, companions, and even the interior behavior of the neutron star itself. This is one of the strange reversals of stellar death. The collapse was violent. The supernova was chaotic. But from that catastrophe can come rhythm. From the death of a giant can come a clock. The first pulsar discovery began as a signal that looked too regular to ignore. Jocelyn Bell Burnell noticed radio pulses arriving with remarkable precision. At first, the pattern was so unexpected that it raised strange possibilities. But the truth was not artificial. It was astrophysical. A rotating neutron star had revealed itself as a beacon. Once one was found, more appeared. The galaxy was not filled with deliberate transmitters. It was filled with compact remnants, each one turning its magnetic geometry into a signal. Now imagine listening not with ears, but with instruments sensitive to radio waves. Each pulse reaches Earth after crossing interstellar space. The galaxy slightly alters the signal along the way, delaying lower radio frequencies more than higher ones. That delay once seemed like an inconvenience. It became a clue. By measuring it, astronomers can estimate how much ionized gas lies between us and the pulsar, and therefore how far the signal has traveled. Pulsars are useful because they are precise, but they are not perfect machines. Some suddenly change speed in events called glitches. A glitch is a small, abrupt increase in rotation rate. It may reveal that the interior is not a rigid ball, but a layered object where a solid crust and hidden superfluid can move differently. This is where the timing becomes intimate. A change in a pulse, arriving across hundreds or thousands of light years, can tell us that something shifted inside a star no one can touch. The crust may have slowed slightly, while an internal superfluid held angular momentum. Then suddenly, some of that motion transferred outward. The distant clock jumped. The change may be only a few parts in a million. But for a neutron star, even a tiny change can carry enormous meaning. Some pulsars live alone. Others orbit companion stars. If the companion is close enough, the neutron star can pull matter from it. The falling material forms a hot accretion disk, spiraling inward through intense gravity. The disk becomes so hot that it emits X-rays. In some systems, the incoming matter transfers angular momentum to the neutron star and spins it up. An old, slowing pulsar can be revived into rapid rotation. These objects are called millisecond pulsars because their periods are measured in thousandths of a second. The phrase recycled pulsar sounds almost poetic, but the physics is direct. Matter carries angular momentum. When that matter falls in the right way, it can give spin back to the compact remnant. The old star becomes a fast clock again. There is a limit, though. A neutron star cannot spin arbitrarily fast. If it rotated too quickly, material near the equator could be flung away, or the star could become unstable. The maximum spin depends on mass, radius, and the hidden stiffness of matter inside. That means rotation is not only motion, it is evidence. If a pulsar spins extremely fast and remains intact, then the matter inside it must be able to support that speed. A rhythm observed from thousands of light years away becomes a message about the deep interior of matter. Now let the view widen. Some pulsars sit inside glowing supernova remnants, still feeding energy into the debris of the explosion that made them. The Crab pulsar is one famous example, the remnant of a supernova observed from Earth in the year 1054. It spins about 30 times per second and releases energy into the surrounding nebula, causing it to glow across many wavelengths. The supernova created the neutron star, but the neutron star continues shaping the supernova remnant. The explosion was not the end of activity. The collapsed core remains an engine. And because some engines are magnetic beyond ordinary comparison, the next part of the journey moves from pulse to field. The neutron star does not only turn, it can also magnetize the space around it until the familiar world of compasses and auroras becomes almost unrecognizable. Bring to mind a compass needle on Earth. It turns quietly because our planet has a magnetic field. That field helps shape auroras and deflects some charged particles from the sun. It is important to life, navigation, and the atmosphere, but it is gentle enough to live with. Now imagine that same idea magnified until ordinary matter begins to behave strangely. Around some neutron stars, magnetic fields can be trillions of times stronger than Earth's. In magnetars, they may be even more extreme. A magnetar is a neutron star whose magnetic field dominates much of its behavior. The field stores energy, stresses the crust, channels particles, and helps produce bursts of X-rays and gamma rays. It is not just decoration around the star. It is part of the star's active machinery. If you could see magnetic field lines, the space around a magnetar would not look empty. It would look structured, twisted, and tense. Charged particles would not move freely in every direction. They would be guided by the field, accelerated through the magnetosphere, and sometimes driven into radiation intense enough to cross interstellar distances. Magnetars can flare. Sometimes they release giant bursts, sending out enormous energy in a fraction of a second. The trigger may involve rearrangements of the magnetic field, fractures in the crust, or a coupling between the solid surface and the field threading it. The details remain an active area of research, but the scale is clear. A small fracture in a neutron star crust does not mean what a crack in rock means on Earth. The material is much denser. The gravity is far stronger. The magnetic stress can be immense. Even a subtle adjustment can release energy that would be catastrophic by human standards. This is one reason neutron stars feel so rich as scientific objects. They begin with familiar forces, then magnify them until the ordinary world disappears. Gravity is familiar. Magnetism is familiar. Rotation is familiar. But in a neutron star, each one is pushed toward an extreme limit. The categories are not always simple. Some neutron stars are ordinary radio pulsars. Some are millisecond pulsars spun up by companions. Some emit strongly in X-rays. Some behave like magnetars. And some objects change their behavior over time, reminding astronomers that these labels describe activity, not separate species carved into stone. A neutron star can be quiet for a while, then brighten. It can glitch. It can burst. It can switch between forms of emission. The compact remnant may look like a simple point from Earth, but its behavior is layered and changeable. To study it, astronomers use more than one kind of light. Radio telescopes listen for pulses. X-ray telescopes watch hotspots and accretion disks. Gamma-ray instruments catch the most energetic emissions. Optical and infrared observations can reveal companions, remnants, or fading merger light. No single picture is complete. A radio pulsar may be faint in X-rays. A magnetar may dominate high-energy bands. An accreting neutron star may reveal itself through bursts from material falling onto its surface. Each wavelength gives a different angle on the same compact mystery. Mass measurements are especially precious. In binary systems, a pulsar acts as a clock moving through orbit. The arrival times of its pulses shift as the star moves toward and away from Earth. Relativistic effects can add further timing signatures. From those tiny changes, astronomers can infer the masses of objects no telescope can resolve as disks. Some of the most important discoveries are neutron stars near or above two solar masses. They matter because a heavy neutron star rules out descriptions of ultra-dense matter that are too soft. If the matter inside could not resist compression strongly enough, such a star would collapse into a black hole. Radius measurements attack the same mystery from another direction. A rotating hotspot produces an X-ray pulse whose shape depends on the star's size, mass, gravity, and light bending. By modeling those pulses, scientists can estimate how wide the compact remnant really is. This is difficult work. The star is small. It is distant. Its atmosphere changes how radiation escapes. Its magnetic field can complicate the pattern, but each measurement narrows the possibilities. Now imagine moving closer to the star again, not as a visitor who could survive, but as a mind allowed to pass safely through the physics. Outside the surface is a magnetosphere filled with charged particles and structured fields. Beneath that lies an atmosphere, if the star has one, thinner than any planetary atmosphere you know. On a neutron star, gravity compresses atmosphere so fiercely that it may be only centimeters or meters thick. The composition depends on history. There may be hydrogen or helium left by accretion. There may be heavier elements exposed or mixed by heat and magnetic fields. Even this outermost layer becomes a clue because it changes the spectrum of escaping light. Below the atmosphere, the surface may become condensed matter, and below that lies the crust. Calling it a crust may suggest something like rock. That picture is too gentle. This crust is made of neutron-rich nuclei and electrons, compressed by gravity far beyond ordinary solids. It may be extraordinarily strong. Simulations suggest neutron star crust could be billions of times stronger than steel. Yet under the star's gravity, even this strength allows only tiny surface features. A mountain there might rise only millimeters or centimeters, while still containing enormous mass. The word mountain changes meaning. On Earth, mountains are high because rock can support height under Earth's gravity. On a neutron star, height is crushed nearly flat. The landscape is pressed toward roundness by gravity that allows almost no relief. And deeper still, the crust becomes stranger. Descend now beneath the crust where the language of ordinary materials begins to fail. The outer layers of a neutron star may contain nuclei arranged in a lattice surrounded by electrons. Deeper down, pressure becomes so intense that neutrons begin to drip out of nuclei, forming a neutron-rich fluid around the remaining nuclear structures. This is already beyond everyday matter, but the descent continues. Near the base of the crust, competition between nuclear attraction and electrical repulsion may create some of the strangest predicted shapes in astrophysics. Researchers call this region nuclear pasta. The nickname is almost playful. Spaghetti, lasagna, gnocchi. But the kitchen language should not make the physics seem small. These are not noodles. They are possible arrangements of nuclear matter under pressures that no kitchen, laboratory table, or planetary interior can reproduce in bulk. Why would matter form such shapes? Because forces are competing. The nuclear force favors certain dense arrangements. Electrical repulsion resists the packing of positively charged protons. Gravity presses everything inward. The result may be rods, sheets, tubes, and other structures, not because matter is trying to be decorative, but because physics is looking for the lowest energy compromise. At the boundary between crust and core, these structures dissolve into a more uniform fluid. Now the neutron star becomes less like a solid object and more like a layered quantum machine. Neutrons may form a superfluid. Protons may become superconducting. Particles can move collectively in ways that have no simple everyday analogy. Superfluidity sounds delicate, as if it belongs only in laboratories cooled near absolute zero. But inside neutron stars, the relevant physics is not delicacy. It is density, pairing, and quantum behavior under extreme conditions. The temperatures may be enormous by human standards, yet still low compared with the energy scales of the particles inside. This hidden superfluid may be connected to pulsar glitches. As the crust slows over time, some internal component may retain angular momentum. When that stored motion suddenly couples back to the crust, the observed rotation jumps. The pulse timing changes, and astronomers on Earth receive evidence of motion buried beneath a surface they will never touch. The core is even more uncertain. At lower core densities, matter may consist mostly of neutrons with a smaller fraction of protons, electrons, and other particles. At higher densities, the possibilities widen. There may be hyperons, particles containing strange quarks. There may be condensates. There may even be deconfined quark matter, where quarks are no longer locked inside individual protons and neutrons in the usual way. None of these possibilities has been confirmed as the true state of neutron star cores. That uncertainty is not a weakness in the story. It is the frontier. Scientists describe the relationship between pressure and density with something called the equation of state. The phrase sounds technical, but the idea is direct. If you compress the matter, how strongly does it push back? If the answer is strong, the matter is stiff and can support heavier stars with larger radii. If the answer is weaker, the matter is softer and may collapse more easily. This is why mass and radius matter so much. A 2-solar mass neutron star tells us that the interior cannot be too soft. A precise radius measurement tells us how compact the matter has become. Together, these clues allow scientists to eliminate some models and preserve others. The star becomes a question written in gravity. How far can matter be compressed before it gives way? What forms can nuclei take? Do quarks appear freely in the core? Where exactly is the boundary between a neutron star and a black hole? Cooling offers another clue. A newborn neutron star begins at temperatures of hundreds of billions of degrees, then loses energy rapidly through neutrinos. Later it cools more slowly, glowing in X-rays and fading over time. Different interior compositions may cool at different rates, because different particles and processes carry energy away more or less efficiently. Observation is difficult. A star's age may be uncertain. Its atmosphere changes how temperature is inferred. Magnetic fields complicate emission. But each cooling curve is another way to ask what lies inside. Now imagine moving back toward the surface, carrying this invisible interior with you. Above the core, the crust holds its strange lattice and possible postaphases. Above the crust, the atmosphere clings in a thin, compressed skin. Outside, magnetic fields and curved space-time shape the path of particles and light. If an object were dropped from far away, it would not fall like a stone on Earth. It would accelerate to tremendous speed, releasing enormous energy on impact. Matter striking the surface could create X-rays, bursts, or hotspots, depending on the system. The surface gravity also alters perspective. Because light bends around the star, an observer at a safe imaginary distance could see regions that would normally be hidden behind the limb. A hot spot might remain visible longer than intuition expects. The star would rearrange its own appearance by curving the paths of photons. Light also loses energy while escaping. That gravitational redshift is not merely a color change. It is a measurement of space-time curvature near the surface. If scientists can measure it accurately, it helps constrain the mass and radius of the star. And yet, despite all this, the object still has a surface. That surface is the difference between the neutron star and a black hole. Radiation can escape. Matter can strike. Signals can leave. The neutron star stands on a threshold. It is beyond ordinary matter, beyond ordinary gravity, beyond any place a human body could imagine surviving. But it is still connected to the universe by light. That connection is fragile. Add too much mass, and the pressure inside may no longer answer gravity. The surface can vanish behind an event horizon. The neutron star can become a black hole. How close can it come before that happens? The answer depends on the very equation of state we cannot yet fully see. So, the hidden core is not a side detail. It decides the fate of the star. Now, place the neutron star in company. Not every compact remnant travels alone. Some orbit ordinary stars, white dwarfs, black holes, or other neutron stars. In a binary system, gravity turns the story from an isolated object into a relationship. Imagine a companion star swelling near the neutron star's gravitational reach. Gas from the companion does not simply fall straight down. It carries angular momentum, so it spreads into a disk and spirals inward. Friction, turbulence, and magnetic effects heat the disk until it shines in X-rays. From far away, such a system may look like a flickering high-energy source. But in the scene itself, matter is being pulled from one star and fed onto another object only the size of a city. The gas accelerates through curved space-time, heats violently, and eventually strikes the neutron star's surface or follows magnetic channels toward its poles. Sometimes, the surface ignites. Material rich in hydrogen or helium can accumulate until pressure and temperature trigger runaway nuclear burning. The result is an X-ray burst, a sudden brightening that announces a thermonuclear flash on the surface of a compact remnant. This is not like a flare on an ordinary star. The burning layer is thin, the gravity is immense, and the surface area is tiny compared with a normal stellar photosphere. Energy that would be impressive anywhere becomes concentrated into a small, dense world. Accretion can also change the neutron star's rotation. As matter falls through the disk, it can transfer angular momentum and spin the star faster. An old pulsar that had been slowing for millions of years can be revived into a millisecond pulsar. This is why some of the fastest pulsars are found in binary histories. The companion loses material. The neutron star gains spin. The system rewrites both lives through exchange. In some cases, the companion becomes extremely light, gradually stripped by the pulsar's radiation and particle wind. Astronomers sometimes give such systems dramatic names, but the underlying process is physical. Energy from the compact remnant removes mass from the companion. The neutron star can also reveal companions by timing alone. If the pulsar moves around a shared center of mass, its pulses arrive slightly early or late as its position changes. From those shifts, astronomers can infer unseen objects. The pulse becomes a measuring tool. This method helped reveal one of the most surprising facts in exoplanet history. The first confirmed planets beyond our solar system were discovered not around a sun-like star, but around a pulsar. Imagine that for a moment. Worlds moving around the remnant of a dead giant, not bathed in gentle sunlight, but orbiting a compact object that sends out beams, particles, and high-energy radiation. Their presence was inferred from tiny variations in pulse arrival times. As the planets and pulsar orbited their common center of mass, the pulsar moved slightly toward and away from Earth, changing how long its signals took to arrive. The discovery overturned expectation. Astronomers had been searching for planets around ordinary stars, yet the first clear extrasolar planetary system appeared around a stellar remnant. It showed that planet formation, or planet reformation, could happen in an environment shaped by a supernova. How such planets formed remains an open question. They may have assembled from material left after the explosion, from a disrupted companion, or from a later disk of debris. If so, they are second-generation worlds, born from aftermath rather than from the original cloud that made the star. Could life exist near a neutron star? Science cannot answer with a simple yes or no. Energetic radiation can strip atmospheres and damage complex molecules. Tidal and thermal conditions may be severe, but a thick atmosphere, subsurface ocean, distant orbit, or old quiet pulsar changes the calculation. The responsible answer is that habitability appears difficult, while the range of possible environments remains broader than intuition first suggests. Neutron stars also travel in pairs with each other. When two compact remnants orbit together, they lose energy through gravitational waves. The orbit slowly shrinks. At first, the change may be almost impossibly gradual. Then, in the final moments, everything accelerates. Picture two neutron stars circling in darkness. Each one is only city-sized, yet each may hold more mass than the sun. They orbit faster and faster, sweeping around each other dozens, then hundreds of times per second. Space-time carries away energy in waves that grow stronger and higher in frequency. The wave is sometimes called a chirp because detector data can be shifted into the range of human hearing. But no sound travels through space from the collision. The detectors measure changes in distance smaller than a proton across kilometer-long instruments. Turning that pattern into audio simply gives human ears a way to recognize the rising frequency. In the last fraction of a second, tidal forces deform the stars. Their crusts, cores, and magnetic fields interact. Matter is squeezed, heated, torn outward, and driven into violent motion. The universe performs an experiment impossible on Earth. It smashes two masses of ultra-dense matter together at relativistic speed and transmits the result through space-time. Human detectors sit far away, waiting for the faint disturbance. From that signal, scientists infer the masses, motion, deformability, and possible internal structure of the stars. This is where the hidden interior becomes visible in a new way. A neutron star is extremely rigid by ordinary standards, but it is not perfectly incompressible. the companion's gravity raises a tidal distortion. How readily the star deforms depends on its radius and equation of state. That effect leaves a subtle imprint on the gravitational wave signal before contact. The final collision may form a black hole almost immediately. It may create a hypermassive neutron star that survives briefly because of rapid, uneven rotation. Or it may leave a longer-lived compact remnant. Each outcome changes the light, neutrinos, ejecta, and gravitational waves that follow. The end of two neutron stars is not just an ending. It is also a forge. As the neutron stars merge, some matter is torn outward at a significant fraction of the speed of light. Some of it is squeezed and heated. Some escapes in tidal tails. Some forms a disk around the remnant. In that debris, neutrons are so abundant that atomic nuclei can capture them rapidly. This is the rapid neutron capture process, or R process. It is one way the universe builds many heavy elements, including gold and platinum. The phrase, "gold comes from neutron stars," is powerful, but it needs care. Heavy elements may be produced in more than one kind of rare event, and scientists continue measuring the contribution from different sources. But neutron star mergers are unquestionably major factories of our process material. The amount can be astonishing. A single merger may eject only a small fraction of a solar mass in newly made heavy nuclei. Small compared with a star is still enormous compared with a planet. The expanding debris glows in a kilonova, powered by radioactive decay as unstable nuclei transform toward more stable forms. The color changes with composition. Material containing lanthanides can be highly opaque, shifting emission toward red and infrared wavelengths. Faster, less neutron-rich ejecta may appear bluer at first. By following the light over days, astronomers infer what kinds of matter were thrown out and how quickly they moved. The glow fades, but the atoms remain. Consider the gold in a ring. Its nuclei may have existed for billions of years before Earth formed. They could have been assembled in neutron-rich debris, scattered into a galaxy, mixed into a cloud, and incorporated into the disk around the young sun. Geology later concentrated some of those atoms into ore, and human hands shaped them into something personal. That story is powerful because it is not metaphor. The atomic nucleus preserves its identity through transformations that erase almost everything else. Stars form and die. Clouds disperse. Planets melt and cool. Civilizations rise much later. Yet the gold nucleus remains gold, a small survivor of a violent origin. The merger may also launch a narrow relativistic jet. If that jet points near Earth, we may observe a short gamma-ray burst. The brightness does not mean the explosion shines equally in every direction. Much of the energy can be focused into a tight cone, so viewing angle changes what the event appears to be. If the jet points elsewhere, radio and X-ray emission can still emerge later as the outflow slows and spreads. A collision lasting seconds at its center can produce an afterglow studied for months or years. This is what happened in a historic way in August 2017. Gravitational wave detectors observed a neutron star merger, and telescopes found light from the same event. For the first time, astronomers could study one cosmic collision through multiple messengers. The gravitational waves described the motion of the compact objects. Gamma rays and the fading glow revealed jets, hot debris, and newly created elements. The same event spoke in space-time, light, and nuclear transformation. This is the modern way of studying neutron stars. No single messenger is enough. Radio pulses reveal rotation. X-rays reveal hotspots and accretion. Gamma rays reveal violent bursts. Neutrinos can reveal the hidden core of a supernova. Gravitational waves reveal motion and deformation. Together, they allow scientists to explore what no spacecraft can approach. Supernova neutrinos are especially important because they escape from regions light cannot easily leave. When a massive star in the Large Magellanic Cloud exploded in 1987, detectors on Earth caught a small burst of neutrinos before the light became famous. Only a handful were detected, but they confirmed that core collapse releases an enormous flood of neutrinos. If a massive star in our own galaxy collapsed today, modern detectors could record thousands. The neutrino signal might arrive before the visible light, giving an early warning that a supernova had begun. It would carry information from the core, from the place where the neutron star is being born. Gravitational waves from a nearby core collapse would add another messenger. Unlike the clean chirp of two compact objects merging, a supernova signal would be more complex, shaped by turbulence, rotation, magnetic fields, and asymmetry. That complexity is not a flaw. It is information. The explosion itself remains an active research problem. The simple picture of a core bouncing and blasting the star apart is only the beginning. Neutrino heating, convection, rotation, magnetic fields, shock waves, and instabilities all help decide whether the explosion succeeds. A successful supernova is therefore not merely a rebound. It is a rapidly evolving system in which gravity, nuclear physics, fluid motion, and particle physics all interact. Those same details can shape the neutron star that remains. The newborn object, called a proto-neutron star, is larger and hotter than the mature remnant. It contains trapped neutrinos at first, then contracts and cools as they escape. Its early seconds help determine its spin, magnetic field, mass, and motion through space. Fallback material may also return after the explosion. It can add mass, bury magnetic fields beneath newly accreted matter, create a disk, or even push the remnant over the limit into black hole collapse. So the birth of a neutron star is not a single clean instant. It is a sequence. Collapse, neutronization, neutrino escape, shock revival, explosion, cooling, settling. The star is born not gently, but through a storm of physics. And after that storm, the galaxy begins the long work of finding it. Somewhere in the Milky Way, countless neutron stars may already be old, quiet, and almost invisible. The galaxy has likely produced hundreds of millions of them over its history. Only a small fraction have been identified. Many do not beam toward Earth. Many are too faint. Many are hidden by distance, dust, or simple silence. A neutron star does not need to be seen to be real. It may drift between ordinary stars, its surface cold, its rotation slow, its magnetic field weakened by time. It may carry more mass than the Sun, while showing almost no luminous face to the universe. How do we find such objects? Often, we find the ones that are not quiet. Radio surveys search for pulses. X-ray telescopes search for hotspots, accretion, and cooling surfaces. Gamma-ray instruments search for energetic beams and bursts. Gravitational wave detectors search for compact objects spiraling together. New radio facilities scan enormous areas of sky with better sensitivity and faster computers. The challenge is not simply collecting signals. It is recognizing patterns inside noise. A pulsar may be faint, intermittent, or accelerated by orbital motion. Its signal may be smeared by interstellar plasma. Software must search across possible periods, delays, and changing motions to reveal the hidden clock. Every new pulsar can become useful beyond itself. A very fast one may constrain the equation of state. A binary one may test general relativity. A young one may reveal supernova physics. A precisely timed one may join a pulsar timing array and help search for gravitational waves from supermassive black hole binaries. In a pulsar timing array, the galaxy itself becomes part of the observatory. Instead of using one detector on Earth, scientists monitor many pulsars spread across thousands of light years. Each one is a clock. If gravitational waves stretch and squeeze space-time between Earth and those clocks, the arrival times of pulses may shift in a correlated pattern. The idea is quiet and enormous at the same time. Dead stars become timekeepers. Their signals cross the galaxy. Tiny changes in their arrival may reveal the motion of objects far more massive than they are. X-ray missions add another kind of precision. They study hotspots on rotating neutron stars, using the pulse shape to infer mass and radius. Because light bends around the compact object, the pulse is shaped by gravity as well as by temperature and geometry. The surface becomes a laboratory for relativity. Future gravitational wave observatories may hear mergers in greater detail. They may detect the high-frequency ringing of a remnant that survives briefly after contact. That ringing could reveal size, stiffness, and internal structure before the object collapses or settles. Perhaps a nearby supernova will send neutrinos through Earth before its light appears in the sky. Perhaps continuous gravitational waves from a rotating mountain on a neutron star will finally rise above the noise. Perhaps future telescopes will measure radii with enough precision to rule out entire families of dense matter theories. Each new signal will narrow the possibilities. Some elegant ideas will fail, others will survive. The core will become less mysterious, not because anyone travels there, but because nature keeps performing experiments and allowing their consequences to escape. This is how we explore the unreachable. We wait for light, particles, and ripples in space-time. We build instruments sensitive enough to notice their smallest changes. We compare observation with theory, correct mistakes, and ask sharper questions. A neutron star may be remote, but it is not beyond investigation. Now imagine one more approach, impossible in practice, but useful for the mind. You are protected from radiation, gravity, vacuum, and speed by technology beyond anything conceivable today. You move toward a neutron star not to land, but to notice what the universe would show if danger were suspended. From a distance, it may not look dramatic. Its visible surface could be faint. In X-rays, hot regions might shine. There would be no enormous globe filling the sky until you were already far too close. The shock would be how much mass is hidden inside such a small outline. As you approach the magnetic poles, beams could sweep through space. They are often drawn as simple cones, but real magnetospheres contain plasma, currents, gaps, and complex radiation zones. The magnetic axis may tilt away from the rotation axis, causing the whole pattern to turn like an invisible lighthouse assembly. The apparent surface would be distorted by light bending. A hot spot might seem to slide around an edge without disappearing when expected. Background stars would shift in position as their light passed through curved space-time. The neutron star would act as a compact gravitational lens, rearranging the sky behind it. There would be no safe place to stand. Surface gravity would flatten matter. The energy of arrival would be catastrophic. Even before impact, the difference in gravity across a body could create destructive tidal forces, depending on the star's mass and path of approach. Magnetic fields could ionize material and guide the particles into violent motion. Radiation would make the environment lethal. The closer you came, the less the word's surface would resemble anything familiar. What would it sound like? In space, there is no surrounding air to carry a roar. But the star itself can oscillate. Its crust and fluid interior can support modes of vibration, just as Earth rings after a major earthquake and the sun resonates with waves. Scientists can translate oscillations, pulse trains, or gravitational wave frequencies into audible sound. The result is not a microphone recording. It is a representation of physical frequencies. Different modes depend on crust thickness, density, gravity, and magnetic field. If identified, they could form a kind of neutron star seismology. This is the wonder of the object. Even when it cannot be visited, it can still be read. Let the impossible visit fade and watch the neutron star across deep time. What happens to an isolated remnant after the supernova debris has thinned, after the bright nebula has expanded, after the pulsar beam weakens? It cools, its rotation slows, its magnetic field evolves and may weaken. The thermal glow fades from X-rays toward wavelengths harder to detect. If its beam no longer reaches Earth, or if the radio mechanism stops, the star can become effectively invisible. Invisible does not mean gone. The mass remains. The dense interior remains. The curved space-time remains. The compact remnant may wander through the galaxy for billions of years, disturbed only by rare encounters. Occasionally, an old neutron star may pass through diffuse interstellar gas and accrete a little material. It may lens the light of a background star through gravity. In principle, such effects could reveal otherwise dark remnants. Finding them is difficult precisely because neutron stars are small. They can carry stellar mass while presenting almost no luminous surface. Our own sun will never become one. It does not have enough mass to build an iron core and undergo core collapse supernova. In roughly 5 billion years, after its central hydrogen is depleted, it will expand into a red giant. Later, it will shed outer layers and leave behind a white dwarf, supported mainly by electron degeneracy pressure. That quieter fate does not make the sun insignificant. It teaches the importance of mass. Low-mass stars fade slowly. Sun-like stars become white dwarfs. More massive stars can collapse into neutron stars or black holes. A star's birth mass sets the range of endings available, although mass loss and binary interaction can rewrite the details. The atoms around us connect these endings. Carbon and oxygen were forged in stars. Many heavier elements came from advanced burning, explosions, and neutron capture events. The calcium in bone and iron in blood are not from space in a vague, poetic sense. Their nuclei were assembled by specific physical processes before the solar system existed. Neutron stars sharpen that connection. They show matter being compressed toward nuclear density and, in mergers, thrown outward again to build some of the heaviest elements. They are both vaults and foundries, places where matter is locked under extraordinary pressure, and events through which matter is released in transformed form. They also reveal the unity of physics. Gravity governs collapse and orbit. Quantum mechanics provides pressure, superfluidity, and strange resistance. Nuclear physics determines composition. Electromagnetism shapes pulsars and magnetars. Relativity bends light, slows clocks, and carries gravitational waves. No single theory tells the whole story alone. That may be why neutron stars feel so rich despite their size. A planet can be explored through geology and atmosphere. An ordinary star can be understood largely through gravity and fusion. A neutron star demands almost everything at once. And there is humility in what remains unknown. Scientists can calculate the collapse of a core, model the pulse of a hotspot, and detect two remnants merging across more than 100 million light-years. Yet they still cannot say with certainty what occupies the innermost kilometers. Knowledge has reached the star, but not finished with it. Perhaps future X-ray observatories will measure radii with greater precision. Perhaps gravitational wave detectors will capture the ringing after a merger. Perhaps a nearby supernova will send neutrinos through Earth before its light appears in the sky. Perhaps continuous waves from a rotating mountain will finally rise above the noise. Nature will keep sending signals. The work is to notice them. As our journey begins to turn homeward, the neutron star recedes to a point. Its surface can no longer be resolved. Its city-sized body disappears inside distance. Yet the meaning remains. That point is the core of a vanished sun. Its atmosphere may be compressed to a thin skin. Its crust may contain nuclear pasta and hidden superfluid motion. Its core may hold particles or phases not yet confirmed anywhere else. Its rotation can keep time. Its magnetic field can disturb atoms. It can feed from a companion, ignite its surface, strip another star, or orbit a second remnant until the pair collide and forge heavy elements. It can host planets. It can cool into darkness while retaining more mass than the Sun inside a sphere the size of a city. And it remains the closest visible kind of object to a black hole without becoming one. Gravity has taken the star almost as far as matter can go. Atomic structure has been dismantled. Nuclei have been pressed together. Space has curved, time has slowed, and light has been redirected. Still, for a neutron star that remains stable, matter answers gravity with pressure. That answer is not permanent for every remnant. It is not fully understood. But while it holds, the neutron star exists on a remarkable threshold. Beyond ordinary matter, beyond ordinary gravity, yet still connected to the universe by a surface and by escaping light. Long after the supernova fades, the remnant continues. It may flash like a clock or remain unseen. It may travel alone or move toward a future collision. Its story is quieter than the explosion that created it, but far longer and in many ways more revealing. The universe often hides its deepest lessons in remnants. The bright star captures attention. The collapsed core preserves the result. It tells us how matter resists, how time responds to gravity, how elements are made, and how catastrophe can produce order. Somewhere in the galaxy tonight, a pulsar is turning hundreds of times each second. Its beam sweeps through darkness whether or not it crosses Earth. Somewhere else, an old neutron star moves silently between ordinary stars. Far beyond our galaxy, two compact remnants may already be spiraling toward a collision whose light has not yet reached us. Their signals travel outward while our planet turns beneath a mild and familiar sky. Here, gravity holds us gently. Atoms keep their spacious architecture. Clocks agree closely enough for everyday life. The extremes of the neutron star feel impossibly distant, yet the same laws govern both places. The difference is not a different universe. It is what familiar physics becomes when mass is compressed almost to its final limit. We began with a point of light. We found a stellar core, a quantum ocean, a magnetic engine, a relativistic clock, and a factory for some of the rarest matter on Earth. And now, as the neutron star fades again into distance, its lesson remains clear. Nature does not run out of wonder when explanation begins. Explanation is what allows the wonder to come into focus. Settle back into the quiet world around you, beneath the steady pull of Earth and the distant light of ordinary stars. Our journey into the heart of a neutron star is complete.